All right, so we're going to end by talking about cis-trans isomers of cyclohexane or any cyclic compound for that matter. These are a different type of isomer. Remember, up until this point, we've just learned about what are called constitutional isomers, right? And those are molecules with the same formula but different connectivity of atoms. So one example would be 1,3-dimethyl cyclohexane and 1,2-dimethyl cyclohexane. Right? Remember, if they have different names, they're going to be constitutional isomers, as long as they have the same molecular formula. They're going to be constitutional isomers of one another. So yes, so these would be an example of a pair of constitutional isomers. So then what are cis-trans isomers? This is now a different type of isomer. This is what's called a stereoisomer. They have the same molecular formula, just like constitutional isomers, but they also have the same connections, all right? Meaning which atoms are bound to which atoms are the same. The difference is the spatial arrangement of those groups, spatial arrangement. So what do I mean by that? Well, I think it's easiest to just take an example here. Here are cis-trans isomers of 1,2-dimethyl cyclohexane. The cis isomer is when the two groups, in this case, the two methyl groups, are on the same side. So cis, I have my two methyl groups on the same side of the ring. This drawing of cyclohexane is what's called a Hawthorne projection. It's really good for showing cis-trans isomers. We'll be looking at this in our chair conformations as well, but nonetheless, this is just like a good way to show what I mean by same side of the ring. Okay. And then on the other side, the other alternative is that we have a trans isomer where the two substituents are on the opposite sides of the ring. So here's my trans, and notice that these two methyl groups, my two substituents, are now on the opposite sides of the ring. Okay. So these are cis-trans isomers. In both cases, I have this methyl group connected to this carbon and this methyl group connected to this carbon. It's the same thing over here too. So the connectivity of the atoms, of the molecule rather, of the atoms in the molecule, are the same. So they are not constitutional isomers, but they are stereoisomers. They have a different spatial arrangement. Both of these, notice, are 1,2-dimethyl cyclohexane. Right? Both of these are still this molecule here, but it turns out that this formula, this drawing right here, isn't actually enough to uniquely describe a single molecule. Right? They're actually, it's referring to two different isomers there, a cis isomer and a trans isomer. There's not enough information in just that structure to uniquely identify a specific molecule. Okay? We can use our wedges and dashes to do that though. So again, this is sort of in contrast to this this would be the 1,2-dimethyl cyclohexane. That's correct, that is what that is, but again, it doesn't uniquely pick out just like a single molecule because it turns out that there are these two stereoisomers. Okay, so it's referring to two different stereoisomers. The cis isomer, where those groups are on the same side, and the trans isomer, where those groups are on different sides. Okay, now again, we can use our wedges and dashes to represent this as well. So representing that they are both on the same side of the ring, we have both of these as wedges, meaning they're pointed out of the board. So the ring's flat, and then you have your substituents pointing out. Versus the trans isomer, which shows that they're in different directions. So one of them's pointed out of the page, and the other one's pointed into the page. So that would be the trans isomer. Notice that if both of these were instead of being wedges, both were dashes, that's also a cis isomer. Okay? So again, our sort of bond line structures aren't quite enough, but our wedges and dash structures can be used to represent stereoisomers. Okay, so now we're going to work on putting this information, this stereoisomer information, into our chair conformation structures. Okay, so one of the things to notice, well, so first of all, which isomer is this, cis or trans? So this is going to be the trans isomer. You have chlorine pointed up and the methyl group pointed down. So actually for this one, I'm just going to walk you through, don't worry about drawing it as much as being able to follow what I'm saying. And then we're gonna do the next example like from scratch where we draw it together, okay? For now, just sort of trust me that I got the right chair going on here. So first of all, yep, draw in the chair, check, check. These carbons are located 1, 2 apart. So that's really the only portion of the chair that I'm gonna have to pay attention to in this particular problem. Carbons 1 and carbons 2. They, of course, have axial and equatorial positions each. But now I wanna make sure that I draw correctly in my structure here. So again, chlorine is pointed up in this drawing. So that means that if it's on carbon 1, it's going to be in the axial position, right? Because carbon 1 is sitting at a peak, which means that its top bond is pointed up in the axial position. The methyl group is pointed down. So which one should that go in, the axial or the equatorial position? Right, so in this case, the methyl group will also go in the axial, but the axial down position, okay? Notice that up was axial when we were talking about this carbon, and down was equatorial because that carbon was sitting at a peak, where it was the reverse situation here where up was equatorial and down was axial. Okay, so notice the difference between those two carbons. Convince yourself that that makes sense. It's because one of them is sitting at a peak and one of them is sitting at a trough. All right, so now I'm going to take this molecule and I'm going to do the chair flip. So what should happen to my axial positions? They should become equatorial. What should happen to my equatorial positions? They should become axial, right? So here we have this chair flip that's going to occur. Again, following my carbons is really hard to do here. The one that it used to be at a peak, now it's got to be at a trough, right? And also importantly, same as before, we have our, just like we were saying before, we have our axial position becoming an equatorial position and our equatorial positions becoming axial. So then looking at this molecule here, or comparing these two conformations that occur from this chair flip, which one do you think would be more stable? Right, so in this structure here, in this conformation here, both of these substituents are in the equatorial position, so this would be the more stable conformation. All right, let's do another example here, and this time we're going to go sort of from scratch. Yeah, actually, most likely these aren't even going to be written in there. It's just going to look like this. Okay. So the whole thing is I need to evaluate which conformation is going to be more stable. I got to draw the more stable conformation, basically. That's my goal. But in order to do that, I have to translate this bond line structure with its wedges and dashes into that chair conformation. So let's work on doing that. First of all, is this the cis or the trans isomer? This is again going to be the trans isomer of 1,3-dimethyl cyclohexane. Okay. So drawing the chair, I'm going to start. Let's zoom in here. I'm gonna start by drawing my parallel lines. Those come to a point. Those come to a point. I'm gonna do the same thing over here because I know I'm gonna have to draw both of them. So I guess we'll get started on this one too. Those come to a point, and those come to a point. Okay, and now one of the things that we got to make sure that we can do is figure out which carbons are which. So I think it's best thing to do is just go in and label. Start this guy is 1, 2, 3. It was up on this side, so it has to be down on this side. 1, 2, 3. Actually, I lied. Start over there. So 1, 2, 3. This one, since it was down, it has to be up on this structure. 1, 2, 3. So make sure you're picking the correct carbons and interpreting that. If it was up in one structure, it has to be down in the other one, vice versa, after the flip. All right, and I have 1, 3 methyl, trans dimethyl, so this one's pointing up on carbon 1. So now I got to draw in my 2 bonds on carbon 1, right? Remembering that if it's at the valley, what's its axial position located? This would be axial down, equatorial out. Likewise, on my other structure, since it's the opposite and it's at the peak, that's axial up and equatorial out. Okay. If I go to carbon 3, I'm going to do the same thing. Does it have an axial up or an axial down? On the left. On the left, it's at a valley, so it has an axial down, and of course the equatorial. After the flip, it's at a peak, so it has an axial up, and it's equatorial. So now I need to figure out where this methyl group is located that's pointed up. Well, it's up on carbon 1, so that's going to be equatorial on this one and axial on this one. And then this methyl group is pointed down on carbon 3, so that's axial on this one, and down is equatorial on this one. Okay, so the question is, which one of these is more stable? Which of these conformations is more stable? Well, in this one, what do we got? We got 1 axial methyl and 1 equatorial methyl. And in this one, we have 1 equatorial methyl and 1 axial methyl. So they're equivalent, right? So in this case, neither one of these conformations would be more stable than the other because they both have the same problem. They both always have an axial group. So in this case, you would say that they are equally stable. One's not better than the other. If we could sort of do a similar problem where if instead these groups weren't equivalent, so this was the original problem on the slide, wasn't 2 methyl groups, but rather 1 chlorine and 1 methyl group. So in which case in this case, which one's going to be more stable? So we got to evaluate. Over here, we have Cl axial and Me, I'm just going to say right? Equatorial. Over here, we have Cl equatorial and Me axial. So which one would be better? For that, we actually have to go back to this table here and see which one's going to have a higher energy penalty for being in that axial position. So in terms of the axial interactions that you would get, the energy penalty that you would get, chlorine is 2 kilojoules per mole versus 7.6 for the methyl group. So you see that there's actually, and you can see this in the ratio as well, it's 70-30 equatorial to axial for chlorine and 95-5 for methyl. So the methyl group really doesn't want to be in that axial position. I mean, the chlorine doesn't love it, but bottom line, if the problem is asking you to evaluate which is going to be more stable, in this case, it's the one where the methyl group gets to be in the equatorial position. Okay. The one thing that I wanted to point out about this was, yeah, the purpose of this slide is to illustrate the fact that these are both trans isomers. But trans isomers and axial equatorial, these are sort of, they're very closely related, but they're not one and the same thing. Just because you're trans doesn't mean you're axial or equatorial axial or whatever it may be, okay? So for in this case, for the trans 1,2, we have one of them is in the axial position and the other one's in the axial position for the trans isomer. All right, when we have the 1,3 trans isomer, one being in the axial position means the other one's in the equatorial position. Okay, so they're different. So it's just it's not quite as simple as being able to say, oh, they're trans, they both must be in the axial position. You got to go through the process of drawing your structure and putting in which one's up and which one's down. Okay. Yeah, so that about does it. It's a pretty complicated chapter, a lot of drawing, so make sure to practice your chair structures, yeah, good luck.